Hello there, welcome back, and a warm welcome to Decaf-Math ASMR. If you are new around here, thanks so much for joining me today. I thought that we could relax a bit, and spend some time together, and I'll talk about metric spaces. Metric spaces. What is a metric space, and what are the key properties or axioms, just general concepts that need to be satisfied in order for something to be a metric space. So, nothing formal, nothing planned. I don't have anything planned at all. I'm just going to be writing on this whiteboard, and it looks like our friend Ross left us a nicely double primed whiteboard with that shiny whiteboard stuff. So I'll just doodle some notes here. Actually, I did plan on mentioning that metric spaces are usually introduced in analysis classes, but today I'm going to be using our XY Cartesian coordinate plane alongside the typical distance formula that we learn in algebra as an example of a metric space. I think it's a great example, and it allows us to do a little bit of algebra review as well, okay, if you're interested in that. But as always, it doesn't matter whether or not you're learning this or if you really care. We're just here to relax together. So if your eyelids get heavy, feel free to just close them, and I wish you sweet mathy dreams. And if you're not quite ready to fall asleep, then I hope that this is relaxing all the same. Maybe you'll catch a tingle or two. Just a relaxing tingle or two in your scalp, in your spine. Either way, thanks for hanging out with me. Let's just get right into it, okay? So, metric spaces. METRIC space. Alright, so how do we define a metric space? We need to have two main things written out or kind of in the back of our minds to define a metric space. The first thing is going to be a set. Okay, a set, which in general is just basically a collection of stuff, a collection of elements together, assuming it's not just an empty set with nothing in it. But aside from that trivial case, visually I might draw something like this just to represent my set. I'll just call it set X, okay? Capital X. And so I have this concept of elements being inside the set and elements that are not, right? So sometimes we can directly write out all the elements in my set. That would be like a finite set with clear elements. So something like A, B, heart, dog, 42. Something like that. The brackets indicate that it's a set. I have 1, 2, 3, 4, 5 elements in this set, and that's it. So that's an example of a collection of elements, and it's finite. There are exactly 5 terms, and I know what they are, and I'm just going to write them out. Other times I cannot do that. So in our XY Cartesian coordinate plane case that I mentioned, that's going to be something like this, R2. Real numbers, okay, real numbers in 2 dimensions, meaning negative infinity to infinity and negative infinity to positive infinity. That whole space that gets spanned there is R2. So that ends up looking like our XY Cartesian coordinate plane. Elements this set is or are points. So this is an element in R2. This is an element in R2. Here, here, wherever, right? Here, here, here. And it goes to infinity in both directions. So I can't write every single point, right? We can have irrational coordinates here. We can have just literally anything. So much stuff. I mean, as long as it's not imaginary, so none of that I business. But with our real numbers, it's the space that gets spanned by R here and R here. So all of these points are going to have exactly 2 coordinates because it's R2, so we're not doing 3-dimensional points, we're not doing numbers on a number line. This specifically is going to be the R2 set, okay? So we can write out a set like this. Other times we can just describe elements in a set. So we can just say the elements in this set are going to be X, where X is going to be names of mammals or something like that, descriptive descriptions for sets. And another example of that would be the set of all sequences that are bounded. Yeah, bounded or something like that. That's one that would probably come up in an analysis class. We don't have to get into it now, but that's an example. So you can't write out all of the sets that are bounded or sequences that are bounded, but we can do a little bit of work with that, and that represents a set of all sequences that are bounded. So that's the idea of a set, okay? And along with that set is going to be a concept of distance between 2 elements of said set. So we want the set itself and some kind of distance that we'll call the metric. And since it kind of represents distance a lot of times, we just call that D, okay? Of course, if you're learning this, you can adapt whatever notation or however, your book or your notes are written. We're just focusing on the main concepts here. But I think this is the most common way that it's written, so that's why I'm using X. But this concept of distance is like a distance function. We want to assign values for the distance between 2 elements. In this case, I would have to write out how we want to assign that. So the distance between A and itself, which we'll talk about, the distance between A and B, A and heart, A and dog, A and 42, and then B and A, B and itself, B and heart. So like every single pairing, we would have to write out this metric ourselves. So we would probably end up making a table like so and pair up everything and then define what the distance is going to be. Other times with the R2 case, for instance, where we have points, 2 points on our Cartesian coordinate plane, we already have a main formula. Like that's the most typical metric for distance. And I'm just kind of scribbling notes here, which is why I'm kind of jumping all over the place. But if I have 2 points, they're going to have 2 coordinates each. So x1, y1, x2, y2. So our typical distance between these two is the quote-unquote length of that line, which is going to be the square root of x2 minus x1 squared plus y2 minus y1 squared. If you've taken algebra, then this might look familiar. It's just our typical distance formula based on the Pythagorean theorem. Something like that, right? So this is an example of a metric. It turns out that this satisfies all the other axioms that are needed. But this would be an example of assigning the distance between 2 elements of R2. In this particular case, it's just general. So if I have, let's say, a point X and a point Y. So there's going to be elements in my big set X. And let's say X has coordinates x1, y1, and Y has coordinates x2, y2. Then I just plug into this, and this gives me a number, right? So if I have like 3 minus 2, and then I square that, plus whatever, 5 minus 2, and I get that, then I get a number here. Sometimes I'll get like square root of 5, maybe I'll get like 12. So it kind of is relative to the length here, the physical length of that. So in this case, I can define my metric in general for any 2 points by using this equation. So sometimes I'll write it by making a table and assigning numbers. Other times I will have a formula, and still other times I'll just have a general concept. So yeah, that's it. That's it with that. So basically, a metric is going to find the distance between 2 elements in my set X, and I'm going to assign a real number to that. So I'm going to have like square root of 5 or something like that to represent the distance between 2 elements in my set X. Now, I don't usually choose to write X and Y per se to represent elements in my set X here, but I think that's actually the most common way it's written. So just be clear that this X and Y are not coordinates of a point, and I don't mean X and Y in my Cartesian coordinate plane. It's just 2 elements that happen to be in my big set X. So I'm going to have a number that represents the distance between them, and once we cover that first axiom, it's going to turn out that and it might be kind of obvious when we think about it, that the distance has to be non-negative. So it's actually going to map the distance between elements to 0 or more. So actually, I think this got cut off, sorry. It's going to map to 0 or more. So it's going to map to a real number, but specifically a number that's greater or equal to 0. So, but that's the concept of mapping. We're going to take the metric, we're going to take 2 elements of our set, we're going to assign a number to it that kind of gives us a concept of distance. So what are we doing? Before we get into the axioms that also need to be satisfied, what are we doing and why are we doing it? So it might be easier to visualize this on like a real number line, just one single number line. What are we doing here? So if we have the set of all real numbers, okay, numbers are just random. Like it's just a random concept. So like, what does this symbol mean? It's just a 5, right? We know it as 5. We've interpreted it as 5. But if I said what is 5? Well, we might start by saying, oh, it's like 5 1 units away from 0. What does that mean? What is the distance, right? So one example of a metric for this case might be, what's the distance between 10 and 11? We might want to use the concept of absolute value, for instance, right? So I might say, well, it's 1 because the absolute value of 11 minus 10, or the absolute value of 10 minus 11 is 1. It's a distance of 1. But that is kind of an arbitrary concept, except that absolute value definition between like x2 minus x1, or 2 elements of the real number, happens to satisfy this criteria, this metric. And the real numbers, the set of all real numbers, is a set, and we have a metric. So it's kind of like the bare minimum structure that we actually need in order to do all the work that we do in arithmetic and in algebra and in calculus too. Is what is the bare minimum criteria that we need to do any kind of analysis here. So it's not just some random metric here. The absolute value is not just some random thing. It happens to satisfy these particular axioms, and when we do so, we can look at it a bit more and do some more analysis on it. So that's the general idea. I think it's really cool because a lot of times if we say like, what does -5 mean in algebra or in pre-algebra or in arithmetic even, when we learn about -5, we might just say, okay, start at 0 and count 5 to the left, 5 5 1-unit things to the left. That's great. Conceptually, that's cool. But what if we zoom out of that even more? What is the distance from -5 to 0? That usually involves our absolute value. But what makes us able to look at that further? What about the absolute value is a good metric for distance? So that's what we're going to get into here. So first of all, that absolute value of the difference, between 6 and 7 or -2 to 5 or something like that is going to be a real number. So we might say, 5 minus -2 is 7. So that would be a real number, and it is 0 or more. Which, by the way, is part of the very first axiom, which is that, there's no particular order for this, but this is what comes to mind for me. So again, if we have two elements in my big set X, okay? Again, not my choice to write X and Y, that's just the common notation. But the first axiom is that whatever metric I have, the distance between two elements must be greater or equal to 0. So we said that, okay? So if I have my Cartesian coordinate plane here, if I have two elements of my R2 set, this distance must be greater or equal to 0. And if you plug into our distance formula, you'll see that it's a positive square root, right? So there's no negative distance here. Also, it's kind of like a second part to this, okay, is that the distance between a point and itself is going to equal 0. It must be 0. So if I just have one point, the distance from this point to itself is going to be 0. And another way to kind of write that is if the two elements are equal to each other, then the distance from X to Y is equal to 0. So these two are equivalent, right? So the distance from Y to Y is going to be 0. The distance from X to X is 0. Remember, X and Y are just arbitrary elements of X. So any element in X, okay? So if the two elements are the same single element, then the distance between them is 0, which is good. You want the distance from 5 to 5 to be 0. That would be a little bit confusing if it's not. And another part of this is kind of the other way around, that if the distance between X and Y is 0, then X and Y must be equal. So in other words, the only way for the distance between two elements of my set to be 0 is if they are the same, right? So these two combined kind of make up an if and only if statement. You can combine them and just say d of xy equals 0 if, but only if and only if x equals y. So this if with too many f's is both directions. So if and only if. So in this case, the distance between two elements is always going to be greater or equal to 0, and the only time it is 0 is if they are equal. And all the other times, the distance between two elements is going to be greater than 0. So this one is kind of the other way around. If I say the distance between two elements is 0, then I would have to conclude that the two elements are the same. So there would be no other situation where if we had two different elements that distance is equal to 0. That would not be the case for a proper metric. So even if we have our xy plane and I have 2 points, the only way for the distance there to, based on our distance formula, the only way for that to be 0 is if they are the same point, and the other way would be if the 2 points are the same point, the distance is 0. So it works both ways, so that's a good thing. And so that's our very first axiom. So we don't have negative distances, and we want to make sure the zero situation is taken care of. So when you make the table with the 5 elements by 5 elements, you want to make sure that the distance from heart to heart is 0, A to A is 0, B to B is 0, but not only that, you don't want 0 anywhere else with any other pairing. Excellent. All right, so I feel like intuitively it seems kind of obvious, the distance between here and here must be 0 or more, but it's cool to think about if you've never kind of taken the time to zoom out there, and it's not always the case, so it's neat to kind of give it some structure. So the next one that comes to mind is some kind of concept of symmetry. So symmetry. So we want the distance from x to y to equal the distance from y to x. Wouldn't it be troublesome if I said the distance from 10 to 11 is 1, but then the distance from 11 to 10 is 5? That would be so confusing. And so if I have, again, I don't know why I keep drawing this, but if I have 2 points in my Cartesian coordinate plane, let's say this is x, this is y, you want the distance from x to y to be the same as the distance from y to x, right? What if this was 5 and then this was 100? That would be terrible. And if you actually plug into the distance formula, because we have squares there, we have x1 minus, or x2 minus x1 squared, and for the y coordinates as well, we can actually go ahead and flip the order, and it wouldn't matter, it wouldn't affect your answer. So that's a good thing, okay? So intuitively that kind of makes sense, but again, that is very important in our structure for a metric. The last one is to satisfy the triangle inequality. Triangle inequality. Okay, you may or may not have heard this in other contexts, but basically if I have the distance from, I need to draw this out in order to write it out correctly, but if I have, let's say, again, using our example of R2, if I have, let's say, here and here, so this is x, this is y, and let's say this is another point z. Again, these x's and y's are not coordinates specifically, these are just elements of our set x, or in this case R2. So if I have 3 elements now, the distance from x to y plus the distance from y to z must be greater or equal to the distance from x to z. That's our triangle inequality, and that's because this makes up a triangle. Let me draw this out. So from x to y, that distance plus y to z, so this distance, must be greater or equal to the distance from x to z, this distance, okay? So in other words, if I look at this picture, the shortest distance from x to z is going to be literally the straight line between them. So that would be this, but if I go x to y first and then add from y to z, that must be greater or equal to this direct distance. And it's only going to be equal if they are all collinear, right? If they're on the same line, then x to y plus y to z is going to be x to z. But other than that, I'm kind of increasing that path, right? The shortest is going to be x to z. So this is the triangle inequality because it makes up a triangle in our R2 space with the typical distance formula, but it doesn't always visually look like this. This is our kind of, this is our R2 representation of it, but any other metric that we define should satisfy this as well, okay? Okay, so that's about it here. If you want to run back through the axioms with the distance formula for yourself, let's face it, probably no one's going to do that, and you're probably asleep by now. That's okay. But if you wanted to, it's kind of a cool little exercise, but we kind of intuitively mentioned it here, and it kind of makes sense if you draw this out. But we're going to generalize this for all sorts of other metrics, and yeah, that's pretty fun. So when you draw out that table with the, like 5 elements by 5 elements, you want to make sure whatever numbers you assign now as distances actually apply all of these axioms. So you want the distance from B to heart to be the same number as the distance from heart to B. You want them to all be greater than 0, except for the ones where it's the distance from A to A and B to B. Those should all be 0. And yeah, you just want to make sure that they all work out that way. So I hope that this was interesting, that you enjoyed the video. Thanks for hanging out with me. I had a great time. Sending you much love. Take good care.